Foundational language models are engineered to predict plausible text across a sprawling, generalized statistical landscape. But against strict historical doctrine, this generalization becomes a liability. To force these models to adhere to a specific cultural domain, engineers typically rely on fine-tuning. This requires curating immense datasets, renting heavy GPU clusters, and expending massive financial resources. Worse, overriding the pre-trained weights with niche, localized data frequently causes the model to suffer from catastrophic forgetting, degrading its baseline ability to reason logically. We can see the ultimate stress test for this problem by looking at the Theravada Tripitaka. This vast corpus contains thousands of dense, ancient teachings, which strictly translates into over 162,000 specific mathematical vectors of context. In a religious context, algorithmically generating a plausible but incorrect doctrine, an AI hallucination, presents an unacceptable cultural risk. The tolerance for error is zero. Standard fine-tuning attempts to bake this vast, rigid knowledge directly into a generative system. When absolute domain accuracy is required, this architectural approach fails. To solve this, we look at the work of Fra Kanin, also known as Kruba Ice. He operates at an unusual intersection. He is an ordained monk at a temple in Phuket, and simultaneously a deep-tech software auditor specializing in AI infrastructure. His target deployment environment is a live, real-world monastic classroom. The resulting system is the Namo Nexus Smart Classroom. It operates as an enterprise-grade Dhammic reasoning engine, structured to bridge ancient teachings with modern inference. The architecture is governed by the ethical principle of Maha Dhamma Dana, a commitment to pure, untainted data distribution, built completely free of commercial interference. His operational thesis is direct: abandon fine-tuning entirely. Instead, achieve strict reasoning and zero-trust security through a rigid, decoupled hybrid cloud architecture. This setup creates a controlled test case for how to isolate a reasoning engine from its knowledge source, a challenge facing any developer attempting to deploy AI within a high-stakes, domain-specific environment. The backend must simultaneously host a massive, culturally complex database and guarantee sub-second data retrieval. This diagram shows the first layer utilizing Google Cloud Storage. It acts strictly as an immutable static vault. This vault holds the raw knowledge base, a dense 239-megabyte face index model containing the entirety of the processed texts. Upon boot, a dedicated synchronization script pulls this heavy model down from the cloud repository directly to the local hardware. The text itself is mapped using the Paraphrase Multilingual Mini-LM L12v2 embedding model. This mapping results in a localized database of 162,895 mathematical vectors. When a student asks a question, the system uses index-flat-IP to calculate cosine similarity. It measures the precise geometric angle between the user's query and the stored vectors. The large language model, in this case Grok's Llama 3.3-70b, is then deployed strictly as a stateless reasoning engine, isolated entirely from the memory function. The mathematically retrieved text from the face database is injected directly into the prompt context, forcefully overriding the LLM's internal pre-trained weights. By restricting the language model to act exclusively as a text processor, the engine forces the output to align with the retrieved vectors rather than the model's own statistical guesswork. With the data pipeline secured, the architecture must negotiate physical hardware routing constraints. This topological map illustrates the local foundation: a Lenovo Edge server, which processes direct inputs from a touch UI tablet within the classroom. The deployment follows a strict architectural rule: keep compute local, keep storage in the cloud, and keep code in GitHub. By running the Faster Whisper speech-to-text module directly on the local Lenovo server, the system eliminates the latency delays associated with round-trip cloud processing. All API keys and environment variables remain physically isolated on the local machine, mathematically eliminating the risk of cloud-based credential leaks. The engineering challenge is taking these highly secure local WebSocket endpoints and exposing them to a wider interface without compromising the firewall. This is solved using a Cloudflare secure WebSocket tunnel, establishing a zero-trust bridge to the outside world. The connection terminates at a Vercel CDN, which globally hosts the static React 18 frontend for the end user. This highly decoupled infrastructure achieves zero-trust security requirements while executing faster and at lower cost than a traditional monolithic cloud application. Beyond static infrastructure, the system operates a dynamic, continuous loop called the classroom pipeline. This module evaluates real-time feedback from the physical environment to adjust the pacing of the lesson. The core of this loop is an evaluation layer known as the emotion engine. This matrix processes classroom inputs through a 5-state detection system, categorizing user engagement anywhere from hyper-focused down to completely disengaged. The transitions between these states are governed by a strict mathematical threshold, a Bayesian prior set exactly at phi, or 1.618. When engagement metrics cross this specific Bayesian threshold, the orchestrator interrupts the data flow and dynamically rewrites the language model's teaching prompt mid-sentence to adapt the delivery. Relying on static system prompts fails in live environments. For an edge system to successfully instruct humans, it must integrate an algorithmic empathy layer to actively throttle its own outputs. The mechanics of the machine reveal a secondary layer regarding the reality of the architect who built it. Modern software engineering exists in an environment saturated with infinite generative tools and highly capable autonomous agent stacks. This environment creates a psychological bottleneck for senior developers, commonly referred to as the builder's dilemma. With zero barriers to expanding a project's capability, developers face immediate scope creep and continuous decision paralysis. Teams routinely reach an 80% completion state across 5 parallel projects, but fail to ship a single finalized product to production. When generative models can write entire codebases on command, raw technical capability has diminishing returns. Execution relies entirely on structural mechanisms that force project closure. The Namo Nexus repository structure operates as an optimized codebase, but its primary function is serving as a deliberate psychological constraint mechanism. Looking at the file tree, the absolute separation of the backend, frontend, and script directories acts as a strict landing protocol for the developer. By enforcing hard physical boundaries, locking compute to local hardware, and storage to specific cloud instances, the architect intentionally removed the option to endlessly tinker with new, distracting cloud microservices. Adhering to this fixed protocol allowed the developer to push the system sequentially from phase 0 all the way through phase 13. The result is a fully deployed system operating stably in a live physical environment. Building a Domic reasoning engine is a complex technical task. But deploying it proves a wider truth for developers. To successfully ship an AI system, you must engineer constraints before you engineer code.